and welcome to Learn Extra Live. I'm Katleho and this is Phil. Hello, Phil.
Hi there, how are you doing?
Great, thanks. How are you?
I'm okay, thanks.
Good. So now we're on grade 12 physical science. Please let us know what we'll be doing today.
Okay, well, we're going to be tackling last year's chemistry paper as a little bit of revision. Some of you guys are writing prelims, maybe preparing for your final. So, Matrix, I think you should get on the page. What do you think?
Okay, that'll be awesome because I know past papers are the most important things that you could possibly do for yourself, eh?
Absolutely. I'm going to jump straight on it.
Please do. So guys, as it's Tuesday, there are also prizes for being here. There is the Casio calculator as well as the Casio labeler. These go out to the most interactive, the most person that participates the most. Maybe you want to say a quote, maybe you have an awesome question to ask. Just make sure that you are absolutely present. The Facebook page is facebook.com/learnextra and our Twitter handle is @learnextra. So those are the avenues that you can send through every question that you have. Stay on the page, guys, because there'll be some nice diagram and pictures that Phil has put up. So make sure that you are actually there viewing everything as we go, because it's going to be pretty much awesome. So make sure that you join us today. Over to you, Phil.
Thanks so much, Kat. Okay, well, Matrix, as I said, today we're going to be taking a look at the November 2011 Paper 2. Now, these papers are for free. You can download them online, but what I'm asking Kat to do is, as we go through them, she's going to be making a cool photo album on the Facebook page where you can actually follow through these questions, because there's a lot of info for one very small screen. So it's actually better if you see it in front of yourself. You can actually print these out. You can download them on your phone. You can download them onto your PC and actually follow through with us. I saw from last week, you guys actually went and made comments under each one of these photos, and you were actually helping each other get to the correct answers. So that's exactly what this page is about. It's all about helping each other to learn extra. Okay, so we're going to jump straight in. Now, I'm leaving some of the definitions out. What I wanted to do, just like last week, is we're going to do a little bit of multiple choice revision. Now, I've noticed when we do matric marking that multiple choice is one of those sections that people kind of don't get right. Now, I just want to go through your ways of tackling this and some of the problems that people have in answering these questions. Now, the biggest mistake that people have when they start answering these questions is that they jump straight for answers, or they start looking in the options for an answer. And that's not the correct way to do it most of the time. You only do that when you absolutely have to. So now the best way to approach multiple choice when we're asked a clean question is come up with an idea first and then start looking through the options to see if something there is the same as what we thought. So let's go through a couple of these examples, and as Kat starts posting them up on the page, I want you guys chatting, but let's get stuck into these questions and let's go for it. Okay, so starting off nice and easy, it says, which one of the following general formulae? Okay, now let me just highlight a few things because some of the words inside here are a little bit intimidating. General formula. Okay, let me just describe what that means for some of you that are just getting stuck into organic studying on what general formulae are. Now, a general formula is a way of coming up with any molecular formula. Now, that means carbons and hydrogens in this case for alkynes. Okay, now let me just remind you what alkynes do. Alkynes, remember, those guys have got triple bonds in between carbons. That means that there's a whole bunch of bonds inside there that would have been going to hydrogen, but they're not anymore. Now they're stuck in between those two carbons. Now the problem is I need to figure out how to come up with a general formula for an alkyne. And the best way to do that is actually to draw the simplest one. And what I'm going to do is I'm going to draw a molecule of ethine. Okay, ethine has got a formula of C2H2. Okay. Well, that's quite interesting. Now, let's see if there's anything which might fit our answer. Even if we don't know the general formula, how can we work it out? Well, let's take a look through here and let's use 2 for the number of carbons. So option A says that if I've got CnH2n plus 2, let's do a quick sum. Then that would be C2H. And if I say 2 times 2 and add another 2, what am I going to get out of this? I'm going to get 6. And that's absolutely wrong. That doesn't agree with our idea of an alkyne. Okay? That, in fact, is a general formula for an alkane. Okay, well, let's take a look at the next option. So let's say C2, okay, 2 times 2 is 4, minus 2 lands us up with 2. Well, that's quite interesting because I see that that actually agrees with what I think. But please, Matrix, don't make the mistake of going, I've got the answer, let's just go on. What I want you to do is make sure that you have gone through the other options just to see if there's something in there that might be right or might make you question yourself. So what I'm going to do is I'm going to go through option C, I'm going to go through option D and make sure that they're not the correct ones, making sure that we got the right one. Okay, so let's take a look there. CnH2n. So let's fill in 2 for C. So 2 carbons, and then 2n means 2 times 2, which gets me 4. Okay, now that's absolutely incorrect. However, that is the correct formula if I'm working with alkenes. Now we're trying to look for alkynes with a triple bond. So option B is still looking good. So let's take a look at option D. So option D says CnH2n minus 1. Well, let's take a look there. So C2H, well, let's put on 2 times 2, which is getting me 4, minus 1 is equal to 3. Now, that doesn't really describe any molecule that I know. So that's definitely not the correct one. We are happy that the idea is definitely B. Now, if you knew this straight away and you learned your work properly, you should actually know that the general formula for an alkyne is CnH2n minus 2. Okay, so let's get stuck into the rest of the questions. I hope that you guys are chatting on the page. I can see that Kat is busy furiously typing away. It's fantastic. Okay, so which one of the following homologous series? Okay, another crazy word there. So let's just see what this word means. Homologous series. Okay, now a homologous series is a family of compounds or a family of organic chemicals which have all got the same structural feature or all have the same functional group. Okay, so now it's telling me I'm looking for a homologous series which does not. Now please, when I see the words does not, okay, now my brain instantly starts to look for the one which does. Now, please be careful. This is not a time to be a rebellious teenager. I'm looking to follow the instruction. I'm looking for the one that does not contain a carbonyl group. And a carbonyl group, just for interest's sake, and you should know this already, has got a C double bonded to an oxygen. So that is what a carbonyl group is. Okay, so let's do a little bit of a revision on which ones these are. Now, here I have no options but to start looking through what they give me. Okay, so let's do a little bit of revision on what an aldehyde, an alcohol, a carboxylic acid, and ester is. Let's give ourselves a little bit of space and let's link it up. So an aldehyde, how do I know I've got an aldehyde? Well, if I've got a C, I've got a double bonded O, and that gets me to an H at the end of a chain. So that means that an aldehyde definitely does have a carbonyl group. Okay, well that means that that's not the one that we're looking for. Please be careful. The language here is very, very complex. So I'm looking for one without my carbonyl group. And there it is. An aldehyde definitely has one. Okay, so now we've cancelled out the idea of aldehydes. Let's take a look at what makes an alcohol. Okay, so now an alcohol. So let's link that up. An alcohol is identified by a hydroxyl. This is quite interesting to me. So I've got a hydroxyl group over here. I don't see any C double bonded O. All of a sudden I think I've got a winner here. So option B looks to be the correct one. But once again, I'm not dead sure. Okay, and Matrix, if you think you're sure, please don't be. Okay, unless you are absolutely, absolutely, absolutely vital and you've seen this question a million times. Okay, just double check, especially if you have time at the end of the paper. Let's just check the other ones. A carboxylic acid. Let's see what a carboxylic acid is. A carboxylic acid has got a C double bonded O with another OH on the end here. Again, we've got a carbonyl group here. In fact, when I add on an OH, this is actually called a carboxyl group. But a carbonyl is there nonetheless. So definitely, carboxylic acids is off our menu. Okay, what about esters? Esters have got something in common with carbonyl groups. Let's just make sure that we know what esters are. Esters have got a C double bonded O and then an oxygen bridge to another carbon chain. Okay, well, there it is. We've got another carbonyl over there, and that's not what we're looking for. So definitely option B as we go there. Okay, so option B is the correct answer for 2.2. Okay, moving along. We're doing pretty well. Okay, we are a couple of minutes into our exam, and let's start taking a look. Now, this is where a lot of matrics get really scared. They see a whole bunch of structures all over the place, and they kind of sort of get scared, and they don't know what they're doing. Okay, just relax. I'm going to show you an easy way to go through all of this. So they tell me that the structures of 4 organic compounds are shown below. Now, there's not a lot which I can see without reading the question. Okay, so it says, which of the above compounds have the same IUPAC name? Okay, now I'm going to give you a little bit of a hint. If you're really smart about this, what you can do is you can identify the beginnings of this without naming all of them. I mean, it's great practice to go name all of these, but naming all of these is worth 8 or 9 marks, and that's not really what you want to do for one of these multiple choice questions. So what I want you to do is to start the IUPAC naming and see if that's an easy way to figure out what's going on. Okay, let me show you what I mean. Let's highlight the backbone, or the longest continuous carbon chain which forms the start of all of these. And let's see if we can identify any patterns. Now, just a reminder that the longest carbon chain can go around corners, and it can go through branches, so please be careful. So what I'm going to do is I'm going to circle the longest continuous carbon chain and see what goes on. Okay, now in this first one, it's quite easy to see that I've got 4 carbons in my longest carbon chain. Okay, that's a good start. Let's go to compound number 2. All right, so compound number 2, oops, let's take a look there. I see 1, 2, 3, 4, 5. Okay, well, 1 and 2 can't have the same name because they've got different carbon chain lengths. So let's see if we can't eliminate some of our things. Well, option A says 1 and 2 might have the same name, and we've just proven that that cannot be the case. That is impossible, because 1 has 4 as its carbon chain length, and 1 has 5. That's absolutely not possible. Let's carry on. If I take a look at compound number 3, I see that there are also 4 in its longest chain. Now that's quite interesting, because that looks like it might be in common with 1. Let's take a look at the last one. Our longest carbon chain over here. Well, our longest carbon chain over here has got 4. Okay, but what can we see? We can see that there's something else different hanging off the sides of our carbon chain. Okay, well, if I take a look at compound 1 and 3 and 4, they've all got something in common. They all have a butane chain as a start. That's because there's 4 carbons. Now, what I'm going to do is I'm going to try and see what else is stuck to the side. I don't even have to go name these. Great stuff. If you do want to go name them, it is great practice, but you're pushed for time, matrix. So let's circle what else is on my chain. I have a methyl and I have a hydroxyl. Well, let's take a look at compound 3. I have a hydroxyl and I have a methyl. Now, that looks very, very similar to each other. Now, let's just compare this with 4. There's something very different on compound 4. This is called a hydroxymethyl, and that's something that we've never named before. But it's also something which 1 and 3 don't have. The only ones so far that have got the same groups off the side and the same backbone are 1 and 3. Okay, if you really do want to go name them, just to make sure, if you think that you're at a final answer here, well, I've got butane as a chain over here. On the second carbon, I have the hydroxyl or alcohol group, so that would be butane, 2-ol, but on the third carbon, I get a methyl. Now, why did I start numbering from this side? Anything which changes the end of an organic chain takes preference for the numbering. So let me just repeat that again. If I change the end of an organic name with ol, ene, ein, those take preference for the numbering. So that would be carbon number 1, 2, 3, 4. And I want you to do this for yourself. This is very good practice. So on the third carbon, I find a methyl. So I've got 3-methyl. Okay, there it is. 3-methyl. And what else? I've got bute. And because it's all single bonded, on the second carbon, I find 2-ol. Now, if you really want a bit of a challenge, try do that again for molecule number 3. So molecule 1 and 3 are the only ones which I can find that are correct. So option C looks to be my 1. Let's just consider the others. B, 3 and 4. Absolutely not. They've got different carbon length chains, okay? Especially when I take a look at the side groups. Okay? 2 and 4. So 2 and 4, let's compare them. Well, one is 5 long, one is 4 long. That is absolutely incorrect. So option C seems to be the correct one here. Okay, I hope that you can see what's going on there. That was quite a tricky one. Okay, 2.4, we're doing pretty well. Okay, so 2.4 says that the reaction represented by the equation below reaches equilibrium. That's pretty important. This reaction is currently at equilibrium. That means that Le Chatelier's principle is in effect. That means that I can use Le Chatelier's principle to predict anything. So I'm told that I've got one of my reactants, which is yellow, one of my products, which is orange. My reactant is a chromate ion. My product is a dichromate ion. The really cool thing about this is you can actually see the color change between the two. If I've got lots of reactants, it'll be yellow. If I've got lots of product, it's going to be orange. So now what we've got to do, let's analyze the question and see what happens. So it says, which one? Okay, please, they emphasize these things on purpose. If it's in capital letters, it means it's really important. Which one of the following changes to the reaction mixture will change its color from yellow to orange? So there we go, yellow to orange. Now, before you even read the options, I've got to decide what I'm looking for. From yellow to orange, what I'm actually looking for is something which is going to favor the forward reaction. Now, let me just show you what I mean by the forward reaction. The forward reaction changes yellow things into orange things. So things which drive the forward reaction or cause the forward reaction to be favored is what I'm looking for. Okay, let's take a look at our options. Okay, so they've given me a few things which do change reactions. If I add a catalyst, does it affect the position of the equilibrium? No, it definitely doesn't. A catalyst does not affect the position of your equilibrium. And here's why. A catalyst does speed up your forward reaction, but it also speeds up the reverse reaction. So they both speed up. But what you'll find is that the amounts of my products and reactants will remain exactly the same over time. Let me just repeat that again. A catalyst does not affect the position of your equilibrium. It does speed up my forward and my reverse reactions equally. Okay, let's take a look at the last one. Option B, add water to the reaction mixture. Well, water is H2O, and I can see that there's H2O inside my reaction. Okay, so now H2O is over here. Ask yourself this question. How would adding more of my products to this reaction mixture change the equilibrium? If I add more water to this equilibrium mixture, let's go through the Le Chatelier steps. Well, the stress is the added water. Le Chatelier says that the system is going to try favor the reaction which reduces or removes that stress. How do I remove water? I favor the reverse reaction, and that's not what we're looking for. So, if I add water, I will favor the reverse reaction, and that's not what I'm looking for. See how a little bit of thought before I tackle this question actually goes a long way. So now let's take a look at options C and D. Hopefully something correct comes up. Add a few drops of sodium hydroxide. This one's a little bit confusing. Sodium hydroxide is a base. Okay, what has a base got to do with this reaction? I don't see sodium hydroxide. I don't see sodium ions. I don't see hydroxide ions. This one is a little bit confusing. But what you can know about a base is that this removes acid. Now, since they've taken out acids and bases, what we can find is that this removes acid. They've taken out acids and bases, and the relevance of that is that sodium hydroxide is going to drop the amount of H+. Now that I do have in my reaction, and there it is. H plus drives the forward reaction. Now, if I remove my reactant, what's going to happen? Le Chatelier says that the system will try fix the problem which I've made. I took away the reactant. The system will try make more by favoring the reverse, and that's not what I want. Okay, well, I'm hoping that option D is my correct one. Let's see if it is. My last option is to add a few drops of concentrated hydrochloric acid. Now, if you've got an acid, what you are actually adding is H plus ions. Okay, well, let's take a look. Are there H plus ions in my reaction? Absolutely. If I look on the left-hand side in my reactants, I see that I'm adding more reactants. If I add more reactants, Le Chatelier says that the system will try get rid of them, and this will drive the forward reaction. That's exactly what we're looking for. Don't know about you, but I think I need a little bit of break, and I think the learners do as well.
Yes,
what do you
they
think?
do. Yes, of course they do. You guys can take a break just to get refreshed, just to get active, just so that when we come back, we have more focus, guys, because this is so important. And if you have that past paper in front of you, it would really help you too. See you right now. Welcome back, guys. I can already see that you guys have joined us, which is very nice. And if you have just joined us, we are doing the prelim paper from last year, hey Phil?
Well, it's the final paper.
The
Actually,
final
this
paper
is the
from
big
last
one.
year. Okay, so this is the big one. Get those papers out, guys. Ask people for them. Download them. You know that there's many sites that you can download them for free. Do as many as you can because they really do help you.
Absolutely.
Over to you, Phil.
Thank you so much. Okay, well, again, we're going to jump straight back into these. Let's get these multiple choice questions out of the way. Let's see if we can move it a little bit faster. I really want to get into the long questions, which is where people really struggle. Okay, now, please, guys, one of these graphs, please don't be scared of it. Okay, it's going to be in your exam, but the nice thing is it's very predictable. Okay, let me explain what we've got in front of us. The Maxwell-Boltzmann curve over here, these energy diagrams. Okay, now they are fairly new to the syllabus. Now, all they tell us is how much of our substance has got the required amount of energy to react. Okay, so let's just pay attention to our axes here. The number of particles and the kinetic energy. So that means that the higher the peak is, the more particles we've got, and the further to the right we are, the more kinetic energy they've got. Okay, well, let's take a look at option A, B, C, and D when we consider which one of these curves represents a reaction with the highest rate. Okay, now inside our description, it tells me that there's this line. This line is a dividing line. So let's just actually make it nice and loud and proud. Okay, so this dividing line, let's just make sure that it lines up perfectly. There we go. That line is the minimum energy required to react. That is the activation energy. Now, a molecule must have more than that amount of energy to collide to make an effective collision. Okay, now what I see if I analyze these curves, if I analyze curve A, look to see that there's a lot of particles which have too little energy. As I go to option B, what happens is my particles start to gain more energy. I'll find that they're more distributed and more of them lie to the right of the graph. Option C, I find that now there's a significant amount of particles which have got enough. But now here is where my interest lies. Option D is the one. Now I'll tell you why. Option D has got a whole bunch of its particles all the way to the right-hand side of that line. That means that they've got more than the required amount of energy. So if I color in the area there, most of curve D actually tells me that I've got enough energy. So this one's actually quite a quick one. We know that option D is our correct one. So option C, B, and A, let's just cross those out. Okay, option D was the easy answer here because it lies furthest to the right, and that means more molecules have enough energy. Okay. Now this one seems to come up almost every year. A certain chemical reaction is represented by the potential energy diagram below. Now I just want you to pay attention to some of the important pieces of information here. I start out with my initial energy. That's the energy of my reactants. I finish up with the energy of my product. So let's just label that. So I start out with my reactants. That's where I begin. Okay, and then I end up with my products. My products lie all the way down here. Now, my reactants and my products have got certain amount of energy inside the bonds of the chemicals. That is something that you cannot change. You cannot change the bond energy of your reactants and the bond energy of your products. That is something that is a result of different chemicals bonded. That cannot change. That's a little bit of a hint. Now it asks me, which one of the following quantities will change when a catalyst is added? Now, I've already told you that the energy of my reactants and the energy of my products is decided by the chemicals. It's not decided by conditions or anything else. So E1 is my reactants energy, E2 is my product energy. Now, let's just take a look at something else. My EA, my activation energy. Activation energy is the energy that's required in the collision between these two reacting particles. So activation energy is something which I can actually influence. I can make things a little bit easier by introducing a catalyst. What I'll find is that I can actually make a slightly different line. I could make a new curve which does that. Notice how it starts and ends in exactly the same place. If I change that curve by adding in a new catalyst, I've lowered the activation energy. So I need you to know that that is what a catalyst does. It lowers the barrier. It makes it easier for reactions to happen. So I find that option C is probably the correct one. Let's just get rid of option D to make sure. Okay. Now I remember I told you that option E, 1 and 2, can't be changed. So the difference between them can't be changed either. Delta H is fixed for a particular type of reaction. Doesn't matter what catalyst you put inside it. So I know that option D is not the correct one. We're getting there, matrix? So hold on tight. Let's keep on going with this. Okay, option 2.7. So let's get into this question. When a metallic atom, okay, let's just take a look at what a metal really was. A metallic atom. Those are the atoms which I find on the left-hand side of the periodic table. It becomes an ion. Okay, well, what's so special about metals is because metals like to make positive ions. So let's read through our options. Okay, how do I make a positive ion? Well, how do I go from having M, which is my metal atom, to being M+? The only way to become positive is by losing electrons. You cannot change the charge on something by adding or losing protons because those are nuclear reactions. Don't even go there. The only thing which you can easily move onto or off your atoms themselves are electrons. Okay, so let's take a look. To go from metal to metal positive ion, what I've got to do is lose an electron to leave behind the positive. So let's just take a look at our options here. So now I think option A might be it. So loses electrons and is oxidized. I think that's right. Now the thing which leads me to think that it's right is because loses electrons, yes, this would make a positive ion. Oxidation is the loss of electrons. Let's just take a look at the other options and see what goes on. Okay, well option B also says it loses electrons, but the loss of electrons can't be reduction. So that's wrong. What happens if it gains electrons? That's wrong. We know that its gain of electrons would make it negative. Okay? And the gain of electron can't even be oxidation. It gains electrons, can't even be. And is reduced, well, reduced kind of agrees with gains electrons, but the only one which is a clear choice over here is option A. Option A has got everything that I need. Okay. Question 2.8. Which one of the following substances cannot, please, guys, okay, cannot, again, please don't be a rebel. They're asking you to find one that can't be used as a fertilizer. Okay, now, this is a little bit of revision on some of the chemical systems that we're talking about. Chemical systems, in terms of fertilizers, we're talking about types of substances which can be dissolved into the soil so that plants can use them. So when I talk about a fertilizer is something which must be able to be dissolved into the soil. Okay, let's take a look at our options. We've got nitrogen gas. Now remember that N2 gas is non-polar. Non-polar things can't dissolve in water. So I think I've got my options straight away. Nitrogen gas cannot be used straight away as a fertilizer. That's why we need things like nitrogen fixing bacteria. That's why we need the Haber process. These all make nitrogen soluble. Nitrogen gas is not suitable as a fertilizer. And that's why plants need other things to get nitrogen for them. Either bacteria on their roots or in the soil, or lightning, or the Haber process, or artificial fertilizers. Nitrogen gas is a terrible fertilizer. It's all around you and you're busy breathing it in right now, but you cannot use that nitrogen. Okay, guano. Now this is a bit of a weird word. Okay, guano refers to bat droppings. Now guano used to be a very, very important source of fertilizer, especially about 100 years ago before they developed the Haber process in great quantities. The guano, or bat droppings, is very, very rich in nitrogen and potassium. Okay, so guano definitely can be used as a fertilizer. It can dissolve into the soil and feed plants. Okay, bone meal. Okay, bone meal is definitely a fertilizer. Now let me just remind you that bone meal is a very rich source for the plants of phosphorus, because bones are full of phosphates. Now bone meal slowly dissolves into the soil, it gives it phosphates, and the calcium in the bones actually neutralizes soil acidity and controls it. So bone meal is actually a pretty good fertilizer to add into a soil. Ammonium sulfate, let's just take a look. Now ammonium sulfate has got that NH4. There we go. There are two of them. Here's your formula. You should know this already. Ammonium sulfate has got lots of nitrogen on it. Now that means that this is definitely a fertilizer. Ammonium sulfate, just as a background, ammonium sulfate is actually a very good way to lower the pH of soil. So some plants, especially pine trees, like to have acidic soils. So I'll use something like ammonium sulfate to increase the acidity. Okay, we're into the last two questions. Let's see what 2.9 and 2.10 hold in store for us. I've got to consider two half reactions below that occur inside a battery. Now I've got to be very, very careful because neither one of these actually fits on my redox table. Okay, so now what I've got to do is I've got to start using my brains here, and I've got to see what's going on in each case. It's all about the electrons, and that's all redox chemistry actually is. If you look to see where the electrons are, that'll tell you a lot. Now in my first reaction I see electrons on the right. In the second one I see them on the left. Now that tells me a huge amount about these two reactions. If I see them written the way that they are, what I can tell immediately is that the top one is that there are a loss of electrons, or that there is a loss of electrons. That makes this into an oxidation half reaction. The second one, I see electrons going in on the left-hand side. That means that I've definitely got electrons joining on with something that is reduction, that is a gain of electrons. Now, I suspect that that might have already answered half of the questions. Let's take a look. Which one of the following statements is correct? So I'm looking for the one which is correct. Let's consider this. Now, it tells me that Ag solid is reduced. Okay, well, let's look to see where Ag solid actually is. I see Ag solid over there. Is it possible that it's reduced if it's a product? It's coming out. That can't happen. Let me just repeat that again. Ag solid is reduced. Now, this is how tricky your examiners are. I see that the silver reaction has got reduction. And I think, oh, I've got the right answer, but that is absolutely wrong. I cannot reduce a product. Okay? ZNS is the anode. Well, if I've got zinc as a solid, it does participate in oxidation. So that actually looks right. Oxidation happens at the anode. That looks to be a good idea. Let's take a look. Silver oxide solid, there it is the negative electrode. That one's quite tricky. Now, what I've got to do is I've got to realize that this reaction is using electrons. It requires electrons to happen. So what starts to happen is that the electrons are being gobbled up. Now, if I gobble up all of my electrons, what I'm going to be left with is a positive charge. If the electrons are going in and they're being taken up by something, I'm going to leave a positive charge. So C is incorrect and B looks to be still the correct one. Then the last one, electrons are transferred from Ag solid to zinc solid. Well, I'm still not entirely sure about this, because this looks like electrons need to go to the silver electrode and away from zinc. I can see that zinc is giving off electrons. There they are. Zinc is giving them away. So this last statement can't be correct. Now, what about our last one? Let's get there. Okay, now this last one is a little bit of a tricky one, all the way back from grade 11. Okay, the oxidation number, oh, this one's tricky, of copper in the compound of CuSO4. Now, let me just show you how to work out oxidation number. So CuSO4, I'm not sure what copper is, because copper is a transition metal. Okay, what I've got to do is I've got to make a small sum. I say copper, because it's unknown, I'm going to treat it just like X in maths, plus, now I know that sulfate itself has got a charge, which I know, and if you can't remember it, just look on your redox table. Sulfate has got a -2 oxidation state. Okay, so I know that sulfate is -2. When I add these two ions together, I must add up to 0, because copper sulfate is a neutral compound. So copper plus -2 equals 0. Let's solve this just like a maths equation. What I'll find is that copper -2 equals 0. And that means that copper is equal to +2. But I think it's time for a short ad break before we get into those long questions. What do you think, Kat?
Okay, let's do that, Phil.
Okay.
So guys, we're going to go for a really short ad break. Someone said on the page, Munaka says, I don't think we need an ad break. I know, I also don't think we need an ad break. But just for your refreshment, please may we take one. See you right after the break. Welcome back, Mindsetters. Wow, I love seeing all the answers on the page. I mean, you guys are going along with every question that Phil's doing, and it's wonderful to see your focus. And it just means that now when you go through the past paper by yourself, you have all the answers and all the explanations. So make sure you're also taking notes. Over to you, Phil.
Thanks so much. Okay, well, just before the break, we ended off with 2.10, some people asking questions about the oxidation numbers. Just a reminder of what's actually going on here. The way that I assigned the oxidation states was I took the unknown element and I added it to the charge, or the unknown, to the known oxidation state of sulfate ion. I added it to the charge of the ion. I made them both equal to 0 if I added them together, because copper sulfate is neutral. What that does for us is that leaves us with an oxidation state of +2. So what I'm going to do is I'm just going to highlight the one which is correct, and I see some of you on the page are saying 2.10 is option C. Now let's just get rid of some of the ones that it cannot be. A metal. Now I can tell you 99 times out of 100 a metal cannot be a negative charge. So that's option A and option B off the table. Now copper itself has got two common oxidation states of +1 and +2, and +4 is a little bit out of the question for something like copper. So what I'm going to be doing is I'm going to be moving on to the long questions now. I hope that you guys join me. I think we're going to have time to squeeze this one last in. I can't believe how time is flying. Okay, so there we go. Let's get into these long questions and let's see what goes on. Okay, so now in question 3 of this paper, what I'm going to find is that I've been given a whole bunch of formulae and a whole bunch of structures. Now, when you're given a big body of intimidating questions like this, what I've got to do is I've got to slow down and say, okay, well, what out of this is actually important? Don't go sit there and try and name all of them. You weren't asked that. So what I'd advise that you do, go look at the questions below, and let's try and go back to those molecules and see if we can figure out what's going on. Now they say, write down the letter. So this is not a lengthy question. This is not one that requires a lot of explanation. So it says, write down the letter that represents the following. Okay, 3.1.1 it tells me that I'm looking for a ketone. Now, if I remember correctly from our first multiple choice questions, let's see what a ketone actually is. A ketone is a C double bonded O, but here's the difference. It is in the middle of a chain. It cannot be at the end, because if it is at the end, that makes it into an aldehyde. What I find is that this, right, that double bonded O on our option D here is definitely a highlight for a ketone. Notice how it's not at the end. So now, see, I'm just going to highlight the same thing in our aldehyde. So if I do the same thing to an aldehyde, option A is an aldehyde. D is a ketone, and that is the difference between those two. If I find the carbonyl right at the end, it's likely that you've got an aldehyde. Okay, so a ketone, let's just fill in our answers as we go. A ketone is option D. A compound, which is an isomer, just remember that an isomer has got the same molecular formula as prop-1-ene. So we're looking for something which has got prop-1-ene. Prop-1-ene has got a general formula of C3H6. The way that I did that was I knew that this was an alkene, and that means that I've got a general formula of CnH2n. Now that helped me figure out what the general formula for propene is. So I'm looking for something with the same molecular formula as C3H6. Now that's quite easy. I can cross out option A. There's way too many carbons. Option B, possibility, but there's too few hydrogens. I found that there's only 4 of them. Option C, I think I might have a winner here. 1, 2, 3 carbons. I've got 2, 4, 6 hydrogens. I've got C3H6. That's cyclopropane. Now you might say, well, how is it possible that a propane is an isomer with a propene? Well, it's because of the ring. You'll find that cyclic compounds are isomers of alkenes. So what do I find there? Option C is the correct one. Let's just make some space there. Option C is the correct one, which gives us an isomer of propene. So let's just put these answers in brackets so that you know what's happening when you're doing these examples. Okay, now 3.2. I've got to do a little bit of challenging here. It says, write down the IUPAC name of the following. Now we've got to do one for compound A and one for compound B. So let's spend a little bit of time on compound A and B. Okay, so compound A, let's first of all identify the longest carbon chain. That's the first step in any sort of naming process. So I can see one which goes there. You could even count around the corner. It's going to give you the same length. 1, 2, 3, 4, 5 gives me pent. Now, because those carbons are single bonded, I find that it is pentan. Now, something special I see on the end of this thing. I see that there is a carbonyl, and it's with an H. That means that I've got an aldehyde. So what I'm going to do is I'm going to say pentan. Now, in the same color, pentanal. Now, you can say pentanaldehyde or pentanal. It's the same thing. They will accept both. Now, that doesn't tell me what happened to the last piece over there. So let's just highlight what else is going on there. I have got a 1-carbon side chain. The question is, do I start numbering from the left or do I start numbering from the right? Now, here is the way you decide. I changed the end of pentane. Because of the al, that's where I start numbering. Pentanal is an aldehyde. So I start numbering from the right-hand side. So that's 1, 2, 3, 4, 5. On the 4th carbon, I find a 1-carbon chain, and that is methyl. So what I'm going to do is I'm going to move this all into a neat place. Let's move it all down there so we can make space for the methyl. Okay, so pentanal. Let's make space for 4 dash, because remember that you've got to make space between the numbers and the words with a dash. So it would be 4 methyl. You don't separate words unless you separate the carbons. So 4 methyl pentanal. So I hope that you can see from the colors, the green is my backbone. That's the one that I started with. I found out which homologous series it was. That tells me that it was an aldehyde. And then on the 4th carbon, I found that there was 4-methyl. Okay, now let's carry on with this. We're looking for an IUPAC name for carbon compound B. Carbon compound B is a little bit easier. So what I'm actually going to do is I'm going to move all of this out of the way. Let's move that name all the way over there, and let's keep it by that compound. Okay, now what I'm going to do is let's name option B. Let's do it the same way. Look for your longest carbon chain. All of a sudden I see that there is 1, 2, 3. 3 gets me prop. Next question I ask myself is, how are they bonded? I see that there is a triple bond. That triple bond tells me that this is an alkyne. So it is prop-ine. Now, is it possible that it could be in another position? Absolutely not. It could be in that one. It would be exactly the same compound. So all I've got to do is say prop-ine. It's not wrong if you said prop-1-ine because it's in the first position, but not necessary. If it's in the first position and you just say propine, that's absolutely fine. Okay, so we've got those two names. Now we're getting there. So it says write down the name or the formula of each of the two products formed with a complete combustion of compound E. Wow, okay. There's a huge amount of crazy words going on here. Let's just try and figure out what's going on. So it says the name or formula. They don't mind which one. Of each of the two products. So we're looking for two products formed when I have a complete combustion. That's our clue. Of compound E. Now, I don't even have to look at compound E before I know what's going on. Compound E is butane. But this is a hydrocarbon. Anytime I burn a hydrocarbon, there's two particular products which always come out if it is complete. And those are carbon dioxide and H2O. Now, just a reminder, carbon dioxide, if you were watching the show before mine, Bruce's, carbon dioxide is a greenhouse gas. Now, they might ask you about that. Okay. Right, we're almost at the end of question 3. I think we're going to have a little bit of time. Okay, so it says compound F is the organic product between a carboxylic acid and ethanol. Write down the following. Okay, so compound F, let's just take a look at what compound F is. Compound F is ethyl butanoate. Okay, now it wants the structural formula of the functional group. Sorry, let's just get there. Sorry, the name of the homologous series first. I've skipped a question there. Let's just go back. The homologous series to which compound F belongs. Ethyl butanoate. It splits into two pieces. That's a very good sign that what you've got in front of you is actually an ester. Okay. An ester has got two parts to the words, and that's a very good sign that you've got an ester. The structural formula, okay? So that means that I've got to draw this out. The structural formula of the functional group. They just want the functional group of carboxylic acids. So they want me to draw the thing which makes carboxylic acids carboxylic acids. So basically what we've got to do is called a carboxyl group. A carboxyl group has got a C double bonded O with an OH on it. It's almost like an aldehyde and an alcohol combined into one, and in fact that is exactly what it is. That is called a carboxyl group. Okay, now here's the challenge. The IUPAC name. Now we've got to do a little bit of detective work of the carboxylic acid from which compound F is prepared. Now I'm going to give you a few clues, and we're going to work through this slowly. Let's first write out the name of that compound. So ethyl butanoate. Now when you're naming an ester, what you've got to do is you've got to realize that the two parts of the name actually come from the two parts which went together to make the ester itself. Ethyl came from the alcohol. So the first part of an ester's name came from the alcohol, and that's where the ethanol came in. They told me that there was ethanol. Butanoate came from the acid. So what they're expecting me to do is to draw out butanoic acid. So let's draw out butanoic acid. So now this one's really easy. All I've got to do is follow my formula. First, bute. Bute tells me that there are 4 carbons, and because it says "and," they are single bonded. Now to make it into butanoic acid, the oic acid means that I've got to put on my carboxyl group onto that last one, and then all we've got to do is fill up with hydrogens, and we are good to go and to get our marks. Now I think we've got time for just the very, very last question before I say goodbye to you guys tonight. So let's just finish off question 3. Now I'm trying to find out what the structural formula of compound F. So they want me to draw out full-on ethyl butanoate. Now this is quite easy. If I take my acid and I put this next to my alcohol and we draw this all together. So let's redraw my acid and let's draw this all together. And what we're going to find is 1, 2, 3, 4 from butanoic acid. So there we go. We've got our hydrogens again. And we're going to have to do this in a little bit of a rush to make sure that we finish on time. I'm not sure how much time we've got left. But let's try and figure out what goes on the other side. What changes when you make an ester is you make an oxygen bridge to the ethyl part. So I hope that you can see that my ethyl part comes onto that oxygen. So we've taken butanoic acid, we've made it into a butanoate. So let's just highlight this. This is the ethyl part, and this is the butanoate part. And that is the last of question 3. And that seems to be a good point to end it off tonight.
Yes,
what do you think?
That is fantastic. Thank you. Thank you, Mindsetters. You were absolutely amazing today. I know that you, Matrix, some of you have written, and you're like, wow, that paper was easier because of mindset. And some of you are still going to write. So good luck to every single one of you guys. Make sure that you're taking notes. Make sure you do past papers galore. Just make sure you get all of them and just sit down and just do them and prepare really, really well, guys, because this is a very important step in your lives. And don't forget, we still have our Saturday show, so don't forget that. Thank you to Liberty also for such an amazing show. Bye-bye, guys. See you next time.